Okay, day 2 of our final exam review. Question number 1, find the zeros of the given function. So we set that polynomial equal to 0 and solve for x. We have kind of two different ways to approach a problem like that. First up is factoring. Don't forget about factoring. Yes, we did learn about the rational root theorem, how to make the list of roots and test them. But if it can be factored, that is going to be your easier bet. So try that first before you just jump into that rational root theorem. When we see a problem like this that has 4 terms, what we want to do first is we want to try factor by grouping. So these first 2 terms share an x squared. I can pull that out front. What's left behind is x plus 2. The second 2 terms both share a 2, and specifically, since that leading term is negative, I'm going to factor out a negative 2. Oh, no, they share more than 2, and 9 does not. 9 is not divisible by 2. Back up. They share a 9. They both share a 9. So I'm going to factor out a negative 9. What's left behind is x plus 2. If these two match, factoring by grouping worked for us. So yay, we factor that x plus 2 out front. What's left behind is x squared minus 9. And that factors again because it is the difference of 2 squares. So we set each one of these factors equal to 0, and we get our 3 zeros. We get x equals negative 2 from the first factor. We get x equals 3 from the second, and x equals negative 3 from the third. There are our solutions. Number 2, find the zeros of the given function. Same directions. So again, we want to think about trying to factor this thing. So we set it equal to 0. And a lot of times students are stumped by one that looks like this. Don't forget, one of the very first things we learned about factoring is a greatest common factor, a GCF. What do those 3 terms all have in common? And they all share an x squared. If we factor out the x squared, what's left behind is x squared minus 4x minus 45. Once that x squared is factored out, we now have a trinomial that we can factor further. Don't lose the x squared. Don't throw it away. It's going to be part of our answer. X squared splits into x times x. 45, I'm thinking 9 times 5. To get that negative 4x in the middle, we need a minus 9 and a plus 5. Set all your factors equal to 0. And don't forget about this one. X squared equals 0. Take the square root of both sides. There's one of our zeros. And then here we get a positive 9. And here we get a negative 5. So there are 3 zeros for that polynomial. Now, sometimes we can't factor by grouping. If we tried this one, what we would see, well, let's just look at it real quick. Don't write this down. This is not what's going to work. But if we tried to factor this one, we pull an x squared out of the first 2 terms. And then the last 2 don't share any common factors. So we could factor out a 1. But notice this and this don't match. So factoring by grouping did not work here. So if we can't factor it, that's when we need to use our rational root theorem. And we have like a kind of a 3-part process for that. The first thing we want to do is we want to list all the possible rational solutions. Those are based on, we call them P and Q. P is a list of the factors of your constant. So here we're looking at the factors of negative 33. We always want to include the positive and the negative of each number we're considering. So plus or minus 1 times 33, that definitely gives me 33. Also 3 times 11. So those are all my factors of 33. Q will be the factors of your leading term, your leading coefficient. Since ours is just 1, that doesn't change anything. So when we do P divided by Q, we just get that list back out again. When we divide by 1, it doesn't change anything. Sometimes when I rewrite it, I like to sort them from smallest to biggest. So these are our possible zeros, possible rational zeros of our polynomial. Once we have our list, then we want to start testing some of those possible values. Test by substitution. So we're going to, if I want to test the value x equals 1, I plug 1 into this polynomial. You can do this with your calculator. This is where I do recommend, if you have the multi-view, that we would want to use that table button, because that allows us to test several x values without having to kind of recalculate things. So we can put in our polynomial x cubed minus 11x squared plus 35x minus 33. Here I do want my calculator to be on ask, because I want it to ask me for x values. I want to plug in the ones that I want to test. Go down to OK and hit enter. I have some numbers in here because I've used this table function before. You can just type right over the top of them. It turns out that 1 was the first value I wanted to test. If I plug in x equals 1, f of x is equal to 8. That's what my calculator told me. I'm looking for a 0 here, so that means 1 is not one of my roots. So next I want to test -1. So let's go to our calculator. Oh, look, -1 is already on my list also. F of -1 is -80, so that's not what I'm looking for. So that's not going to work. So how about next up, we test x equals 3. So like I said, you can just type right over any of those x values. I type 3 and hit enter. And yay, 3 gives me 0. That means two things. That means x equals 3 is one of the solutions or zeros of my polynomial. It also means that x minus 3 is one of the factors of my polynomial. Once I find one of my solutions, then I like to go ahead and do my synthetic division. The result that we got, x equals 3, goes in the box in the upper left. And then the coefficients of my polynomial, 1x cubed, -11x squared, 35x, and -33. For synthetic division, we drop down that 1, don't change it at all. And then we start multiplying the number below the line times the number in the box, goes in our next missing space. Add those two values. The number below the line times the number in the box goes in the next missing space. Add those two values. Multiply and add. We better get a 0 here because that matches this 0. That's not what we wanted. I mean, it's good. It checks out. But what we really did this for is to get these coefficients. So remember I said x minus 3 is one of our factors. And the rest of it factors into 1x squared minus 8x plus 11. Okay, from there, we want to solve this part. We need to figure out the rest of our zeros. This one, I can actually tell by looking, is not going to factor. So if we need to solve a quadratic that can't be factored, we are going to use the quadratic formula. So we want to go back in here, say x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I would say you can use your calculator to simplify this. Minus a -8, that becomes +8. We get 64 minus 44 under that radical. 8 plus or minus 64 minus 44 is 20. Sorry, square root of 20, don't lose that. Square root of 20 does simplify. 8 plus or minus 2 times the square root of 5 over 2. And we can reduce or simplify here. Be careful, make sure you divide both terms by 2, not just the leading term, not just the 8. So we get 4 plus or minus the square root of 5. So now terminology, our zeros are x equals 3, that's what we found in step 2, and x equals plus or minus the square root of 5. Those are our zeros. Our factored polynomial is x minus 3. And usually, if the factors involve a square root, we usually just leave it factored over the rational numbers. So I would write it like this. I like that factorization. If you wrote it out with those square roots, that is not wrong. That is fine too. It would be x minus 4 plus the square root of 5 and x minus 4 plus, oh, sorry, 4 minus, change the sign there, plus or minus 4 minus the square root of 5. And that would be another form of our factored polynomial. Number 4, we move on to our rational functions and graphing. This one we don't actually have to graph. We're just going to answer the question about asymptotes. Find your vertical, horizontal, and oblique asymptotes. So in order to do that here, we are definitely going to need to do some factoring. The top doesn't factor, that is just 5x squared, so we'll leave it as we see it. The bottom does factor. X squared is x times x. 20 factors of 20 that give me a negative 12. So 20, I think of 4 times 5, but 4 and 5 can't get me 12. So how about 2 times 10? That gives me 20. And if they are both negative, that does give me the negative 12. And negative 2 times negative 10 is positive 20. Great, that works. Okay, so vertical asymptotes. Vertical asymptotes occur where your denominator is 0. So we get one vertical asymptote here at x equals 2. We get another vertical asymptote here at x equals 10. Those are our two vertical asymptotes. For horizontal and oblique asymptotes, we consider those kind of together, horizontal and oblique asymptotes. Both of them are based on the degree of our numerator. The highest exponent we see in our numerator is a 2, x squared. The degree of our denominator, might be easier to look at the unfactored version, is also x squared. When the degree of the numerator and the degree of the denominator are the same, when they match, we have a horizontal asymptote at y equals, and we look at the coefficients of those two leading terms. So up top, our x squared had a coefficient of 5. On the bottom, our x squared had a coefficient of 1. So we have a horizontal asymptote at y equals 5. If we have a horizontal asymptote, we automatically have none for our oblique asymptote. You can have one or the other, but not both. So since we found a horizontal, there is no oblique. Number 5, same question, different function. So let's take a look again. Before we go too far here, I just want to factor and see what our function looks like in its factored form. Up top, I can pull out a 4. On the bottom, I can factor that. X squared is x times x. 18, let's see, 1 times 18, 3 times 6, 2 times 9. But it's that 2 and that 9 that'll give me that 7 in the middle. I will need a plus 9 and minus 2. And look at that. It's a good thing I factored, because guess what this is? This would be a hole in our rational function. So before we find any intercepts, we want to cancel out those common terms and reduce our function. So this is what we want to use for the answering our asymptote questions. So vertical asymptote, again, happens where the denominator is 0. Vertical asymptote and degree and domain go hand in hand. So x equals negative 9, there's our vertical asymptote. Horizontal asymptote or oblique asymptote, oblique or slant asymptote, those are two names for the same thing, oblique and slant. Again, degree of the numerator compared to the degree of our denominator. We'll use our reduced form. The degree of the top is 0. We don't have any variables up there. The degree of the denominator is 1. It's x to the first power. Anytime the top is smaller than the bottom, automatically that tells me I have an asymptote at y equals 0. And again, if there is a horizontal, that means there is no oblique.